Hello, my name is Max, and I'll be presenting my paper critique today on the paper Large Language Diffusion Models from 2025. So this is a paper, and essentially they challenge the idea that it is possible to create a diffusion model which outputs similar results to that of large language models, which rely on autoregression. However, my first thought when reading this paper for the first time, start to finish, was there was no possible way that this was discovered out of a vacuum, nor all the components they decided to implement in this paper had come out of a vacuum. In my opinion, it's too niche, novel, and cool. Because of this, I wanted to give a quick run through as to what led up to this paper. So firstly, yes, you truly can understand the nature of this paper without knowing what came before it, nor some of its fundamental concepts. So firstly, let's just quickly run through what led up to this, and we'll start with diffusion to deep learning applications. So in 2025, this paper was published called Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. Essentially, what they wanted to do was continuously add Gaussian diffusion to, say, data. As you can see, there's a spiral example, and see what they could do after diffusing it to try to reconstruct the data back to something that was well understood and close to the original shape that it was trained on. So, say, for example, here, a way that this could be applied was to try to figure out, given an image, what you can do from a missing component to try to reconstruct something that would look correct. So A, B, C, A is original, B is the noised image, and C is what's reconstructed. So fast forward from 2015 to 2020, researchers continue having more fun with images. In 2020, this came out for denoising diffusion probabilistic models. Similar concepts. So can we, take something that's pure noise and reconstruct it back to an original image using the same training we saw before from A to B to C, but with the objective of just going from B to C. So something here that they did, and this was discussed in class, was trying to reconstruct that image given a noised version or a slightly deformed version. Now we're going to fast forward from 2020 to 2022, entering the language of large language models. Les Burt of 2018, that was an important piece, but we can just skip over that for all intents and purposes. In 2022, Diffusion LM was released, which showed improvement in controlled text generation. Same process as we've been familiar with. They're learning embeddings through this process. And it was found to be possible to create a language model using diffusion, but it was very rudimentary and nothing so novel as to move forward with it in the way that our autoaggressive models were moved forward with. But again, the same principle applied from 2015 to this last paper. So diffusion. Fast forward to 2024, the members of this paper critique published many items in this field. So one of those was a mass text diffusion model. They call it an MDM, which finally had established scaling laws. There's also now this concept of reverse curse as they've created this diffusion model. And one thing I want to emphasize here is that this paper is essentially what the paper critique is based on, but they just scaled it. They didn't really reference what was discussed in this paper here. And I really can't look at both of them separately in the same sense that I really just view them both as the same paper. And there's an important piece of this which must be referenced in order to fully understand the paper critique itself. So here they essentially created an MDM out of 1.1 billion parameters to try to compete with very relevant language models for its time. When they were training it, they clearly had a scaling law, but one of the biggest drawbacks was 16x required more compute. You can see the flops as well for parameters where they look very comparable, but again, 16x more compute for comparable parameters for models that outputted very similar results. And now is this concept of reverse curse, which diffusion models were found to solve very well for. So around this time, in the shape that our language models were, So say it was trained on information went in the form of A is B, it had trouble figuring out the reverse relationship that B is A because it moves in a left to right sequence. One big difference that diffusion models solve for is that it generates everything at once. So this concept of linearity doesn't really need to apply, and it's something that it can break. And in the primary 2025 paper that we're looking at, this is an example which they give via Chinese poems, where they're able to reconstruct these poems in ways that GPT really struggled with. So with that all out of the way, we can finally look at the paper holistically. So enter the large language diffusion models. And so like we said in the beginning, they created a specific diffusion model, which they called LADA, that they aimed to compete with general LLMs for their times. And at this time, Llama 3 was very relevant, and Llama 3 8B was their comparison. And yes, they also included supervised fine tuning when training LADA. So they first start with a question, just to refresh. Are the results of LLMs special because of the architecture or because of the focus on getting intended output? So the question of generative modeling. So everything that we discussed before would tell us, yes, it is possible to get these results because we're going after intended output and not because LLMs are so special in their architecture. So here they establish a general formula for generative modeling, and they make the comparison to autoaggressive modeling. Later on, they go to discuss how exactly they're going to formulate what it looks like with diffusion, but again, enter their specific model, large language diffusion, with masking. A little difficult there with the A. Interesting way to name it, but LADA is easy to say regardless. So here are the results of their trained model. So we see Llama 2 7B. For all intents and purposes, we could ignore that. It's not a great comparison. Then we have Llama 3 8B and LADA 8B. So LADA 8B and Llama 3 8B have quite a bit of overlap. There's clear regions where LADA excels, and there's clear regions where Llama excels. So this benchmark was for zero few shot. I don't want to say that they're cherry picked in the sense of they knew which ones would perform best to make LADA look the best. But the general model itself does perform well, regardless. And so, similar to what we had before with images, where we might go from A to B to C for image, take a piece out, and then try to reconstruct it. What they did is masking with their tokens. So let's say we have a sentence, we tokenize it, and we train it on what the intended token is, but sort of like with diffusion, we take out components. So we try to reconstruct out of this masked process what the original output is, and in that, try to create some sort of general generative model that might give the LLM properties that we're used to. So in this approach, the core of LADA is a mass predictor, with that said. And here they formulaically write out what it looks like with their loss and training and what they're looking for. Yes, it's very straightforward in the sense of cross entropy loss is a huge part when it comes to comparing the mass tokens. And their results are pretty good given this benchmark that we're seeing here. So yes, I will also note on the side that they were trained with many H800s, or this model was trained with many H800s. So you'll see the LADA 1B and the LADA 8B. The LADA 1B is what their paper from 2024 created, and the LADA 8B is what they created in this paper, essentially. So what we can see here is, for training tokens, for flops, and the benchmarks, they look good. They obviously use a lot of tokens to train them. And scaling laws are very real. And the quickest way to glance this is just look at the first row, look at the last row, look at the middle row. There is a clear linear progression here. So far, we seemingly have an impressive model with good performance. We have diffusion applied training that works. Um, and there's a substitution of autoaggressive formulation for generative modeling principles and single pass generation of results rather than iterative output like we're used to with ARM LLMs works given what we're seeing with these benchmarks. Not to mention, we clearly have scaling laws that work. So the idea that we could apply more compute to get better results with a higher parameter model is very possible. Supervised fine tuning empirically works. So there's ways to improve the model post training, and their benchmarks are seemingly real comparisons. I'm going to emphasize seemingly, as we'll get to that later. So if we look at scaling for Lada in its baseline and these benchmarks, we can clearly see that the more flops, the better the results. You don't really see anything fall off. You see things go up and to the right, and that's indicative of we can throw more at it to get more out of it. And like we said before, with the supervised fine tuning, this was a process that which they added. It worked. We can go into it later and what it looked like. But yeah, so they're really just feeding the masked response and just making sure that they can get their intended results. So benchmarks here for the post training, so post SFT, we can see Lada, Lump 3, Lump 2, Quen 2, Quen 2.5, Gemma 2, DeepSeek. The model and its type, so diffusion versus everything else that's autoaggressive, the amount of training tokens that were used for the training, SFT when applied, and SFT and reinforced learning, the benchmarks and everything else. So this is really just a lay of the land to say, it works, here it is, this is what we have. There's room for improvement as well. So they trained their competing autoaggressive models with tokens that they chose. So this is sort of self-constructed in their baselines when making these comparisons to other models. And I think that there's room for improvement in the sense that they could instead rely on, say, their production grade version of their competitors when making these comparisons. There's data differences between what was trained, so it's not exactly one for one in terms of what these models fully understand across general reasoning. We don't have RLHF, just SFFT, and there's no KV cache as it's not applicable to this architecture, which is fine. But there's no extra system level optimization. So there's no specialized attention and there's no general consideration, as we might have seen with like flash attention with specific improvements when it comes to compute or let's say the NVIDIA platform with their H100s or H800s that we're trained on. So with all that said, what's really the catch? Some aspects of the proposed model have glaring issues, and in my opinion, are overhyped. So in this 2025 paper, they ignored, I think they referenced very small in the appendix, but they ignored the 16x compute requirements versus their autoaggressive model competitors. That's a wide gap and something that's not very feasible when, say, a company is strapped with only so much cash and time and power that they can work with. The benchmark comparisons were confounded. They all made sure that they were self-constructed, and there might be an aspect of dishonesty in that where it's not exactly one for one, and nor is it the best one for its competing models. And the generative modeling principles thesis is less novel than presented, which is an emphasis of their paper, as it was already discovered by this group in 2024 and some papers before this. However, their overall discoveries are real and substantive in the sense of the reversal curse is real and structurally inherent to autoaggressive models, but they do solve for it very well. And they discovered this on better text to be compared because they were able to scale the model. Infilling and constrained generation are natural strengths, of course. Scaling curves are real. I'd rather say scaling laws rather than curves, but there's nuance in how they describe it in the paper. And the industry has continued, yes, to put investment into the field. So DeepMind, ByteDance, Inception Labs, not necessarily saying that it's the best thing to put money into, but it is something that is having money put into it. So here's a quick example of a sample process um, of a prompt, a question, and the result it came to. So it can clearly reason, and the fact that it has the ability to do multi-round dialogue in this use case, which they include in their paper. However, it's something that's not necessarily useful or clearly excellent when it comes to these diffusion models when compared to the ARMs. So since being published, what have been the ripple effects? Applications for code generation, improved speed. So there have been applications made, and there have been improvements made to this model. So top to bottom, LADA native, this is what we have. So tokens per second, 0.9, not good, not usable, not good. But they had improvements. So LADA, slow, fast, cache, this variant, 55 tokens per second. Now that's readable and that's optimized. As we can go down, we can see some insane numbers. So Inception Labs, Google, and ByteDance have published their proprietary models using Diffusion. I've never used them, but those are impressive numbers. So here's Inception, DeepMind, and ByteDance. So overall, the contribution from a lot of paper is significant and real. That can't be discounted. Diffusion for language models is niche, but it's an interesting paradigm. It's not something that's going to be deployed to, say, a production instance to run all of your language model needs, but it can be used for some things. It does not beat the mainstream models in all-around intelligence or application, but there's a future where perhaps there's a hybrid of models in the sense that I might need code-generated. This diffusion model might be able to do it very well at some insane token per second rate. And I might have points that are skeletons, which my ARM model created that then is filled in after that's generated. It would be interesting, but that's just an idea. And so personally coming away from this, I have to wonder if there's an area of hardware optimization around Gaussian math that can be explored. I don't know if that's possible. It's just a question. But if so, it would make that 16x compute gap a lot smaller. So the final score of this paper is a 4 out of 5, as ultimately someone had to do it, someone had to write it, someone had to test it, and they did it. And here are some questions for the class, and we can pause here. Thank you.